are still cleaning up, feel free to keep cleaning up.
How do you import new
I can show you after class. Yeah, it's really easy to do on a Raspberry Pi, honestly, because Linux systems are built to code. Love Linux systems. All right. So, fun fact, next week I have jury duty. So, next week we aren't going to be able to do, I'm not scheduling any labs because quite frankly, I don't even know if I'm going to be here at all. And I won't know until I can call in on Friday of this week. But I've just given to the point where like, I don't want to have to change my plans on Friday afternoon about what we're doing next week. I'd rather set it up in class. So next week, we do not have any labs scheduled. I will record videos for Tuesday. If I'm here on Thursday, I will expect you to show up, but we will have a very long lecture. So I'll probably live stream it. You can just sleep at home if you really want to. But we're only having lectures next week. That's why I'm trying to get the labs done this week, putting a little bit higher priority on this, okay? All right, let's jump into class material because we only have like 20 minutes. Okay, so we talked about capacitors and inductors. We did some discussion on both of those pieces. Now, I did not give an extensive discussion on it. I do expect you to read the textbook. The textbook has a lot of information on the topic. Specifically, if you will need any help with working on your problems, the textbook is a good place to start. I make you buy and read a textbook for a reason, okay? That's part of it. Okay? But I'm not going to say like, oh, don't ever come ask me for help. But it's really, there is no way I can cover every piece of content in this class verbally. Some of that material you do have to read elsewhere and get on your own, okay? And if you need to come in and ask questions because it just doesn't make any sense to you, I'm going to ask you if you read your textbook, if it's something that I didn't cover in class, and if you did, if you just say yes, we'll talk through it, okay? This is a hard class. I'm sure all of you are aware of that by now. Zane just nods. All right, so what we're going to be talking about now is first order systems. Okay, so when we go back and we look at what we did in the last chapter, this is, by the way, chapter 4. When we talked about the last chapter, what we found was that if we plug a capacitor directly up to a voltage source, it charges immediately. Similarly, an inductor charges immediately. In a DC current circuit. Okay? Meaning that the moment that switch is flipped, the moment the power supply is turned on, the moment you have some kind of a connection. Duncan's not here today.
No.
Those guys are going to have to do the lab together. Oh well. But the moment that connection is made, what you have is you've already got it set. It's already in the circuit. You can figure out what the voltage and the current is. Now, the problem is this is not realistic. There is a finite amount of time that it takes for any capacitor to charge. In order for either of these to happen, what you end up looking at is, like let's say, for example, we look at the capacitor charge, okay? And here this will be the voltage versus time. And the voltage versus time graph, assuming this is the branch where there's no voltage being applied from the power source, and then here a flip is switched and the capacitor is charged, you have an immediate jump in voltage. Now the problem with that is that we have the relationship between current and voltage in a capacitor. What this says is that the change in voltage multiplied by C is equal to the current. Here we have an infinite slope, meaning if we were to graph out the current versus time for this, here is where it starts, the power supply comes off. At this point, we flip the switch to connect the capacitor. We have an infinite current. And then it goes back to 0. That's not realistic. First of all, you can't have an infinite current, ever. And second of all, we know that due to parasitic effects, the capacitance of the capacitor is not exactly perfect as it is. Okay? So really what we get into is there is a finite amount of time at which this voltage charges the capacitor. There is. It is not infinite. It is not immediate. And as a result, there is a finite amount of current that travels in the circuit. What we need to do is we need to be able to calculate what that is. And what we're going to do is we're going to study an RC system and an LR system, both of which are first order systems, in order to give us some information about how fast these components charge. Just as a hint, this is chapter 4 is where I did that one like problem that went all the way across the board. We are getting there. In fact, we're there. I don't know if I'm going to have time to do it today, but we're going to talk some basic concepts. All right. So, basic concepts. I have a DC source. I have a capacitor. I have a resistor. This circuit is grounded. Okay? Go to your room. Dang it. This will be VS. This will be C. This will be R. Now, qualitatively, as I said, you're not going to be able to say, okay, we're going to plot the voltage across the capacitor with time. Qualitatively, let's say we have a switch that at time equals 0, that switch is connected. Basically, that's when we plug it into the circuit. Okay? If we assume the capacitor starts with no charge on it, then it's going to be starting with a voltage of 0. Okay? After a certain amount of time, that capacitor is going to charge. Right? It should be charging. We have current flowing into it. We have current flowing out of it. That's going to charge the capacitor. So if we look at t as it approaches infinity, we're going to see a very interesting behavior out of this circuit. What is going to be the maximum charge on that capacitor? Is it going to be like something relative to R? Well, we got to think about a few things. Okay? The biggest piece here is KVL. What does KVL say? What is KVL? It's the loop equation that says sum of voltages in a loop is equal to 0. Okay? So what this means is, according to this circuit, Vs has to be equal to Vr plus Vc. Has to be true. There is no way that that cannot be true. This has to be true at all times t. Even though this is constant, these probably will not be constant. Okay? Now, we also know, according to Kcl, what is Kcl? It's the current equation that's at nodes. We know that Is, the amount of current coming out of the source, is equal to IC is equal to IR. All three of those components have the same current. Okay? These two sets of equations form our constituent equations for the circuit. Okay? Constituent equations. We also have our component equations. What is the relationship between voltage and current in a resistor? V equals IR. It's Ohm's law. So VR is equal to IR R. That's one of our component equations. If we know what the voltage is across the resistor, we can find the current through that resistor. It's what we just did in the LED lab. Okay? On the flip end of it, the relationship between current and voltage in a capacitor is IC is equal to C dVc dt. Okay? And those two are our component equations now. Now these are all of the equations we need to solve this system. But this does have some very challenging problems. At t equals infinity, is this capacitor still going to be charging? It should be at its steady state value, right? Anybody know what steady state means? Not changing. It's homeostatic. It's stable. Okay? Oh, I was going to talk about transients first. All right, we should probably talk about that. Nice. If you've done your reading assignment, you should have already written down the definition of a transient. Okay? Anybody know what a transient is? Anybody done the reading assignment already? Do you know what it is? That doesn't help me at all. It's a homeless person. Okay? All right? Do not
lasting for a short time.
Give alcohol. Oh, yeah, that's right. Okay? A transient is a short, time-dependent response. Basically, what a transient response is it's what happens when the system is not in equilibrium. Okay? How many of you have ever had a betta fish? They do. If you have a tank with more than one fish and one of them is a betta fish, it is not in equilibrium state. That's just sick. What were we going to say, Ivana? I like goldfish. I have a goldfish that I got like 10 years ago. I bought it for 10 cents from Petco.
You have a silver fish? Is it huge?
It's huge.
My buddy has one with a baby kite, and it's like the size of a good sized bass if you catch on the lake.
Yeah, well, mine's like this big.
I have one that's got like that big.
Yeah, that's what we
That's insane.
Or around there. I had to put it in my pond and just got the video.
Okay. Nice. Heckin' chonka. All right. So what we have with a transient response is the system is not in equilibrium. Okay? This represents like, it could be anything from a switch is flipped. which causes the system to go start from one behavior and then transition into a different behavior. This could be something where a power supply changes. Goes from one constant value to another constant value. This could be anything from, if you go look at real life, we have transient responses. If Matt and I are getting into a fight, and I push Matt, and Matt goes flying across the room, okay? That's a transient response because Matt doesn't just keep flying across the room. Eventually he's gonna hit the wall. I know I'm swole.
I have a question though. Where did the homeless people?
If you Google the word transient,
Yeah, it's the second definition.
it's the second definition. That's where it comes from. It's me playing with words. It's because I'm a terrible person. So, my bad.
Chat, flip it. Flip it, chat.
We'll have to put that on the.
No! No! That's not okay.
What does transient mean?
What did you say?
So would it be wrong though?
It's the wrong definition. I tell you exactly where you should get the definitions from the book, okay? But this could represent any change. Okay, you plug in a component, you randomly charge a capacitor and plug it into a system. There's going to be a transient response. Okay, and what that means is for a short amount of time, the system is going to behave differently. And the key to a transient response is that it's going to be approaching equilibrium. And here, we call equilibrium steady state. Okay? When you're all at rest, you're all at steady state. When you get up out of your chair, you're experiencing a transient response to you standing. Your body's CG does not suddenly pop up. There is a time-dependent response between you getting out of your chair and being at a natural height above the ground. All right? So the whole goal of this is there's going to be some change. When we flip this switch, there will be a change. This system will want to go towards steady state. That's what we want. So if we go back and look at this equation system, we want something that is steady state, something that is not changing, okay? Something that is constant, something that is stable. When that happens, are we going to have any current in the system?
No,
Why do you say no?
because if we're going on for infinity, that makes the time equal to 0 for the UET.
That's correct. If we don't have any time-changing response, if this is truly steady state, then your dVc dt is equal to 0 at steady state. Which means we do not have current in the system. If we do not have current in the system, how much voltage is across your resistor? Why is it 0? Because if you have no current through a resistor, you can't have a voltage. Yeah. So that's what you have. At steady state, all of the voltage in the system is across a capacitor. There is no voltage across the resistor. And why is it? It's because this relationship has to be true. There is no current. Sorry, Seth. Okay, we can't have current at steady state. Now that's going to be a very weird behavior. It's going to result in a very different behavior because do we ever have current in this system?
The start,
Yeah. For a very minuscule amount of time.
We're going to have to because at some point this is going to start with a voltage at 0 and at some point it's going to end up at this value of Vs. it has to go from there to there. There has to be a change. There is a change in voltage, meaning there has to be a current. But at the start, there's no current, and at the end, there's no current again. That's kind of weird. What we end up finding out, and we'll derive this next class, what you end up finding out is this is an exponential function that looks like that, where it very rapidly changes the voltage, and then the change in voltage slowly decreases over time. If you plot the current, IC versus T, you end up with something that looks like this, where the moment the switch is flipped, the current jumps up to some value. There is an infinite change basically in the current, but we can do that because nothing wrong with that. But then the current value slowly decreases to 0, okay, to the steady state value of 0. Any questions on this? I still have you for like 3 more minutes, so we're going to draw another circuit. All right, now my new circuit is going to look like, oh, by the way, this circuit, at steady state, the capacitor behaves as an open circuit, has the exact same behavior. If you want to analyze your system, treat your capacitors as an open circuit for a DC source. That's how they behave. Okay, it makes it a lot easier to look at the circuit. I'm going to go ahead and just replace this with an inductor. Okay, L. Here, our KVL values haven't really changed. Vs is equal to VL plus VR. Our KCL values haven't really changed. Is is equal to IL is equal to IR. And then our component equations, we still have the resistor. VR is equal to IR times R. That's still the same. But we have that new component equation. The component equation for the inductor is not the same as the resistor or the capacitor. It is VL is equal to L DIL dt. Okay, so that's really the only change between this system and the other system, is just this one component equation. Now, instead of graphing out VC and IC, we'll change this to VL and IL. And what we want to know is, how does this system behave at steady state? Do we have any current in this system at steady state? Why do you say no? Oh, right, I forgot to erase that. My bad. Thank you for pointing that out. Different graph, different life. Do we have any current in the system at steady state? We didn't for a capacitor. We actually run into a problem. Is there any voltage across the inductor at steady state? If there is voltage across the inductor, there has to be a change in current. There's not going to be a change in current at steady state. At steady state, the change in current, DIL dt, is equal to 0. Because of that, VL is equal to 0. At steady state, there is no voltage across the inductor. Do we have current flowing in the system? We have to, because this relationship is true. At steady state, Vs is equal to Vr. Which means we have current flowing through the inductor, but the inductor has no voltage across it. all of the voltage in the system comes out of the resistor. So, at steady state, the inductor acts as a short circuit. That is correct. Yes, but I like explaining it. Okay? If we were to plot these out, this will be the last thing and then you guys can go. Sorry to hold you. We know at the very beginning there's going to be a voltage across the inductor because there has to be a change in current. Which means our voltage looks something like this. And our current looks something like this. Which, by the way, this approaches Vs over R, which is the voltage across the, well, it's the current through the resistor at steady state. This is the relationship we have. We'll notice these are exactly flipped from what we saw for the capacitor. They are exact inverses of each other. I'm going to do a giant problem on Thursday. It's your problem, not mine. So you have homework that's due, I think you have a reading assignment that's due Thursday. I didn't post your quiz until like last night, so it's due this Friday. Yeah, good luck.